the participants to this session, afternoon session, where we will discuss Reynolds transport theorem, introduction to Reynolds transport theorem. So, at the outset, I will tell you before going to the Reynolds transport theorem, classification of systems. We should know first these things as a prerequisite for studies of mechanics of fluids. These are very important, that systems are basically of three types. One is control mass system or closed system. These are two synonymous names, the control mass system or closed system, which usually we refer to as system. When we tell system without any prefix or adjective to it, we mean control mass system or closed system. Another one is control volume system, which we call simply as control volume, and another is isolated system. Let us find the definitions of all these three and what are the characteristic features that distinguish one from the other. Now, for a control mass system, it is a fixed mass of fixed identity contained within the system defined by the system boundary. So, with this system, since the identity of the mass is fixed, therefore, no mass flux takes place across the system boundary. That means, no mass comes into the system, no mass goes out of this system. So, mass remains constant by amount and also by identity, but the energy can cross the system. That means, the system interacts with its surrounding by energy flux across the system boundary in terms of heat and work, as we know in thermodynamics. Whereas, a control volume is defined as a quantity of mass in a fixed region in space where we keep our attention for studies, but not with fixed identity. This itself means that when the identity changes, means the mass will cross the control volume boundary or the surface of the control volume. So, therefore, the main difference here with this system is that mass flux takes place across the control volume boundary or the control surface, which is not the case for the fixed mass, that means control mass system or closed system. Okay. Energy flux also can take place across the control surface. Now, the question comes whether the mass by amount will remain same or not. That may remain same, may not remain same. When the mass flux coming in equals to the mass flux going out, then the amount of mass will remain same, and that is precisely the steady state of the control volume, when the control volume mass is invariant with time. But these two fluxes, influx and efflux, may not be same, and in that case the difference between the two will indicate the change in mass. If influx is more, then mass will increase; if influx is less, the mass will decrease. Isolated system is a system that does not interact with the surrounding either with mass or with energy in terms of mass or energy. That means, it has fixed mass, fixed identity and fixed energy. That means, no mass flux, no energy flux. So, therefore, the isolated system and control mass or control closed system, the difference is that the closed system mass is fixed, identity is fixed, but energy is not fixed, because there is an energy interaction with the surroundings. But in isolated system, energy is fixed. That means, isolated system is a system which does not interact with the surrounding at all. So, nobody is interested with isolated system. It is by definition we have to know, but this isolated system comes into consideration afterwards. In the studies of thermodynamics, we take system and surrounding together we consider as an isolated system. That means, interacting systems together may be considered as an isolated system. This all details I am not going now, because this is now beyond the scope of our studies at present. Now, we will be interested in this two control mass system and control volume system. Now, next I will tell you one very important thing. What is Reynolds transport theorem? Now, let me tell you like this. Basic laws of physics relating to conservation of mass, conservation of energy, conservation of momentum, all these basic conservation laws or any other laws of physics, for example, the first law is nothing but the conservation of energy, first law of thermodynamics. These are all basically defined with respect to a system, means control mass system. For example, we always tell the conservation of mass, the mass of a system is constant, is conserved. Okay. So, therefore, the conservation equations is defined with respect to a system. For example, if you define the conservation of momentum or Newton's second law of motion, we define the rate of change of momentum of a system or system under consideration if it is squeezed so that its mass tends to 0, we call it a particle. Okay, the rate of change of momentum of a particle, rate of change of momentum of a system, of a substance means system, equals to the force acting on it. Now think of a control volume. Control volume may not move, control volume may be fixed, will be maybe fixed, may move, but may not move. For a fixed control volume, how do you define the rate of change of momentum? System always moves in a flow field to maintain its identity, just like the Lagrangian particle. So therefore, we cannot define the rate of change of momentum for all control volumes, because control volumes may be fixed, may be moving. So therefore, this statement of conservation of momentum, that rate of change of momentum of a system, that means refers to a system, equals to the force acting on the system. So therefore, we see this way the basic laws of physics, the conservational laws, are all defined with respect to a system. But how do you relate these laws applied to a control volume? Why? This is because, why we want this? This is because in engineering applications we have to deal with control volume. You will see when we analyze engineering equipment, the equipment is fixed. There is a continuous flow coming in and going out. For example, a gas turbine, a jet engine, where the fluid comes in from one side, goes out from the other side. There are different equipments in a power plant, boiler, condenser, turbine, compressor. So therefore, when we analyze the engineering equipments or engineering processes, we have to deal with the control volume analysis, because there we have to consider the control volume system which is fixed, where the mass flux takes place across the surface. So therefore, a relationship is required which will convert this statement applied to a system, these basic laws of physics, to that of a control volume. Sometimes I am telling you it comes from intuition. For example, mass, mass of a system, system means again control mass system is constant. This is the definition of the control mass system. But if I tell you that if there is a fixed control volume, what will be this conservation of mass? This of course comes from intuition, for which you do not have to take help of any theorem. It is very simple. The inflow of mass and the outflow of mass is there, and the balance between the two will tell what will be the accumulation of the mass, which has been told by Professor Suman Chakraborty. That means the rate of outflow of mass minus the rate of inflow of mass is the rate of decrease of mass within the control volume. So therefore, this way we can formulate the principle for control volume just by intuition in case of mass flow, but in case of momentum flux, when control volume is fixed, along with the flow the momentum will come in and momentum will go out. This may be linear momentum, this may be angular momentum. What will be the case for energy? So all these conservation laws to be defined with respect to control volume, from that with respect to system with which we are acquainted, is known as Reynolds transport theorem. So therefore, Reynolds transport theorem makes a link between the fundamental conservation laws applied to a system to the laws applied to a control volume. Okay. Now I start the derivation of Reynolds transport theorem. Let us consider at any time t in a flow field a control volume CV and a system both coinciding with each other, but to make a distinction I make this dotted boundary thing as system. System means the control mass system, and the firm boundary line is the control volume. At any time t they coincide each other, and this is in a flow field. Just I show it by this velocity vector. That means in a flow field we define at any instant of time t a control volume and a system shown by dotted line coincide with each other, and we consider the control volume to be fixed. So we at some time interval t plus delta t, at some time interval t plus delta t, let us have the fixed control volume like this. Okay, this is the control volume, and the system, let us think that the system goes like this. System has moved somewhat, that means this is the system at time delta t. System has moved somewhat in this direction in the flow field, the same flow field is there. That means now this is the position of the system where the control volume remains same, the farm line. Now at time t, when control volume and system coincides with each other, I define this space, that means the volume rather, by this 1. 1 is the volume that is contained by control volume and the system which are coincident. Now after a time delta t, small interval of time, system is displaced like this. Now after this displacement, it has caused some intercepted volumes. I just show this by red ink, intercepted volume. This volume, let us consider first the volumes are defined like that. This is volume 2, unintercepted volume. This intercepted volume is volume 4. Okay, this is volume 3 rather. From here if we start, that intercepted volume, let this volume is 2, this intercepted volume is 2, this is 3 and this is 4. Let us define like that. That means when the system has gone, it has created 2 intercepted volume. This side the volume which is given by 2, I write that 2, this is volume 2, this volume is 2, volume 2 we represent, this volume just you see is 3 and this intercepted volume is volume 4. That means volume 4 and volume 2 are intercepted volume with the fixed control volume by the system due to its advancement in this direction depending upon the flow velocity vector after a time t plus delta t. So based on this background of system and control volume, now let us proceed with this. Let we define n as any extensive property, n as any extensive property. Well, any extensive property which may be mass itself, which may be momentum, linear momentum, angular momentum, energy, and let eta is defined as this extensive property n per unit mass. That means it is the corresponding intensive property, the intensive property corresponding to the extensive property n, any extensive property, and eta is that extensive property per unit mass m. Now we want to relate the conservation of this n with respect to system to that with respect to control volume. How to do it? Let us now write the rate of change of the property dn dt within the system, dn dt in the system. How do you do it? It is nothing but the system is now you see comprises volume 3 and volume 4 at t plus delta t. So we can write n 3 at t plus delta t plus n 4 at t plus delta t minus n 1, that was n at 1 at time t divided by delta t, limit of that as delta t tends to 0. That means the property n contained within the system at time t plus delta t minus that at t divided by delta t tends to 0. Now what I do, I make a very simple algebraic manipulations in the right hand side. What is that? I add and subtract this thing n 2, that means this volume is 2, this intercepted volume N2 at time t plus, because this volume is created at time t plus delta t because of this movement of this system, divided by delta t as delta t tends to 0. That means I just add and subtract this one in the right hand side and rearrange the term little bit and write this d, rather here dn dt system. Now I rearrange it in a way that I take this here and this out. So first I write limit, little rearrangement, n3 t plus delta t plus n2 t plus, because we have added this delta t, minus n1 t minus delta t as delta t tends to 0. Then what is left? This is n4 is left out. So, this becomes limit n4 at t plus delta t divided by delta t tends to 0, and I have added this n2. So, I have to limit, you have to deduct this, subtract this n2 t plus delta t divided by delta t tends to 0. So, you see that dn dt system becomes then limit, then means what happened? I have added this and subtracted this. This I have taken with this, then this remains as it is, minus limit n to t plus delta t dt. Now, you see what is this term? Try to understand what is this, what does it represent? n3 plus n2. Now, n3 plus n2 means the property n contained in the control volume at what time? T plus delta t, and n1 is the property in the control volume at time t, because at that, in this situation, control volume and system coinciding each other. So, therefore, this term is nothing but the control volume n in control volume at t plus delta t minus n in the control volume at t divided by delta t limit delta t tends to 0. That means, this is nothing but the rate of change of n in the control volume. So, this rate of change of n in the control volume can be written as del t of, now if we consider now rate of change of this within the control volume. Now, this property within the control volume at any instant, if we try to find out, it may so happen that the property eta per unit mass will change, which means this property may not be uniform throughout the control volume. So, it may change within the control volume. So, therefore, it is always better to write in the integral form. That means, per unit mass rho into dV is an elemental mass, dV is an elemental volume of the control volume, it is the density of the control volume for that elemental volume. So, if eta, that means n changes within the control volume, in that case we can write this way, that means this integral over the control volume tells us the property n within the control volume, and this rate of change for the control volume which is fixed here is the local change, that is why I give del t. That means, this term, this first term, that means this term together is nothing but the rate of change of n within the control volume, which can be written mathematically this way, when the property n is varying within the control volume. This we take in general. If it is constant, then we will come out, it will come out. So, simply integral dV will be the volume of the control volume. So, this is the rate of change of property n within the control volume. Now, what is this? what is this? Now, this is the big question. We have to understand what is this. Before that, let us see first conceptually what are these two quantities. You see, this is the quantity, this means the property n within this intercepted volume. Now, when delta t tends to 0, this intercepted volume tends to 0. That is the approach. That means when delta t tends to 0, try to understand this. Here is the concept that the control system coinciding the control volume like this at the initial time t. Understand? That means when this intercepted volume collapse, then what is the meaning of limit this n divided by delta t at delta t tends to 0 at that time? Similarly, when delta t tends to 0, this volume collapse. So, what is the meaning of this instantaneous value of n within this intercepted volume divided by delta t tends to 0? When this is collapsed, that means this volume actually coincides with the surface of the control volume. When this volume collapses, this surface, this system, this dotted, this coincide, this part of this system coincides with this. That means this volume becomes equal to this part of the surface. So, therefore, you see that these two terms have got some special significance. So, to understand this, let us go through this. Let us go through this, how to understand this thing. Let us, oh, a teacher has to do this thing. Let us understand this. Let us consider a control volume like this, a control volume. Let us consider a control volume. Let us consider a elemental area dA here, and let us consider the outward normal is this, the area. This is the unit vector representing the direction, positive direction, outward normal direction. Let this is the velocity vector in general, which may not be along the normal to the area. You already know that rho, if density is defined here rho, v dot product, this already you know after our so many lectures dA, this quantity represents the mass flux across this surface. Now, let us consider a velocity field like this, a velocity field. So, over a small elemental area, this is the flow velocity. So, this is nothing but the mass flux or the outflow rate of mass flow rate out of this surface dA from the control volume. This already we know. Now, if we multiply this with eta, if we multiply this with eta, what does it indicate? It indicates the rate of outflow or rate of efflux, same thing, rate of efflux of n from dA. That means rate of outflow from the area dA, or rather I should write not from dA, over the area dA, over dA from CV, from CV. That means this is the rate of outflow or rate of efflux of the property n, because n is what? N is eta into m, or rather eta is n by m. So, that means eta into this represents this. That means what does it physically signify? That since there is a flow, in a flow, when there is a flow velocity defined, along with the flow many properties are also flowing. Obviously, when you have a flowing stream, mass is flowing with it, energy is flowing with it, momentum is flowing with it. So, if you define a fixed control volume where the flow comes in and flow goes out, so along with the flow mass comes in, momentum comes in, energy comes in. Similarly, the mass goes out, energy goes out, momentum goes out. So, therefore, the flux of this property n over this surface. Now, if we integrate this eta over the outflow area, that means if we specify some outflow area, a outflow area where the velocity is going out of the control volume, velocity vector is such, then over this outflow area, then this is rate of outflow. I am not writing is again rate of outflow or efflux of n over the entire outflow area from the control volume. That means again I am writing rate of outflow or efflux from control volume, because it takes care of all outflow area. Similarly, if we write this, now if we have an inflow area, that where the things are coming in, so eta into rho into v dot n dA over the inflow area will tell you the rate of inflow of the property n of n, rate of inflow or influx property n into the CV, Now question comes, you may ask, how do you know the outflow area, inflow area? Doesn't matter. You see that if you sum up these two, let this is A, this is B. Now if you sum up this A plus B, that means if you do the integration over the entire control surface, over the entire area of the control surface A, then what it will give? Let us first see if we can recognize an outflow area. The difference is that in the outflow area, the velocity vector and the outward normal are in the same direction. See, whereas in the inflow area, the normal direction and the direction of the velocity vector are opposite. So therefore, this product V dot NDA and V dot NDA, if this is positive for outflow area, negative for inflow area, that means if we algebraically add it, make the algebraic addition, so that we do not bother which is the inflow or outflow area, you simply integrate over the entire surface area. So depending upon the direction of the velocity vector, it will take care of that. That means there may be entire outflow area, there is no inflow to the control volume. There may be entire inflow, no inflow to the control volume. There may be both inflow and outflow, which will be automatically found out by the positive and negative value, and if we algebraically add this, that means over the entire area, this will represent, which is very important, net outflow or efflux rate of n from CV. That means it is the rate of efflux of outflow minus rate of influx or inflow of n into CV. That means net outflow rate, net rate of outflow or net rate of efflux or efflux rate of n from CV. Now here also you see this thing represents, now you understand the physical significance. When this volume collapses, this represents the rate of outflow of n from the control volume, and this represents the rate of inflow of n to the control volume, and as a whole these two represents the rate of net rate of outflow or efflux of n from the control volume. That means this plus this with a minus sign, because here we do not take care of this, here sign is automatically taken care of, that is why this 2 plus makes this. So this is substituted in place of this 2 is substituted by this. That means this minus this represents the net rate of efflux of n from the control volume. Now I write this thing like this, you can understand that this takes more time. This is the time determining, time rate controlling process, that this one. Now you see we write therefore dN dt for the system equals to, now we have already found this is eta rho dV over Cv plus what is that net outflow, that means eta rho V dot n dA over the control surface. Now, this is the Reynolds transport theorem. So, before stating the Reynolds transport theorem here, I will tell another one very important thing here. You see one thing, while deriving this equation, what we have done, we have, for example, the velocities when we define here, the velocities have been described with respect to a coordinate system. Let us consider the coordinate system x, y, z, and in this analysis we have fixed the control volume. Control volume is fixed. That means when we reference the velocity or describe the velocity field v with respect to a coordinate system to which the control volume is fixed, or it can be told other way, the reference coordinate system is chosen or control volume is chosen in such a way that control volume becomes fixed with respect to the reference frame, which means the reference frame is attached to the control volume. Why? Because control volume may move also. It is not necessarily, it is a general case, control volume may be fixed, may be moving, but the same analysis can be taken to be holding good, it will hold good. That consideration of that, the frame of coordinate system is attached to the control volume, because in our derivation we have kept the control volume fixed with respect to the coordinate system in which V is described, which means this is a coordinate frame which is attached to the control volume. With this logic, we can write in case of moving control volume, which takes care of both moving and static control volume, this as the Vr, that is the relative velocity with respect to control volume. This is Vr, that means eta rho Vr dot n dA. Okay. So, now what is this? This is rate of change of n, rate of change of n within the system What is this? This is rate of change of n within the control volume. Within the control volume I am writing Cv, and this is net rate of outflow or efflux, net rate of outflow or efflux from the control volume, and this is valid for any extensive property n, and this is known as Reynolds transport theorem. Reynolds transport theorem. Okay. Now, if the control volume is at steady state, that means under the situation of steady state this becomes 0, because no property changes with time within the control volume. So, therefore, we can write that Reynolds transport theorem for steady state is dn dt, that means rate of change of property n for a system equals to only the efflux eta rho. I have already told that this is the relative velocity with respect to the control volume dot n dA over the entire control surface. So, this is only for steady state, and this is plus this, it is the unsteady state. This is the Reynolds transport theorem. This links the phenomena which changes with phenomena of changing a property n within this system to that within the control volume. Okay. Now, let us have some now let us have some, that takes terrific time. Now, let us have some example. Again I write the Reynolds transport theorem system. Again I write system, because in the same page it is better. It is the rate of change within the control volume rho dV over the control volume plus the net rate of efflux rho eta Vr dot n dA. N is the unit vector directed along the outward normal of the area dA over the entire control surface. Now, let a case conservation of mass. How what is Reynolds transport theorem looks in case of conservation of mass. Now, in case of mass is the property, then n is equal to m. What is eta? Eta is 1 m by m. So, therefore, we write d. So, we can use the Reynolds transport theorem for conservation of mass like this, dm dt system is equal to what I can write here, del del T of rho dV over the control volume plus eta is 1 rho Vr dot n dA over the control surface. Now, what is dm dt for system? Dm dt for system is 0 by definition of the system. So, therefore, this is precisely, that means del del T of rho dV Cv plus integral rho Vr dot n dA Cs is 0, and this is precisely your integral form of continuity equation, that is the rate of change of mass within the control volume, this is the mass within the control volume plus net rate of efflux or outflow of mass from the control volume equals to 0. I told you at the beginning this comes from intuition, but this is derived from the Reynolds transport theorem. This is the conservation of mass. Now, let us solve some problem with this conservation of mass. Some example I am giving how again we can use this Reynolds transport theorem to the conservation of mass principle. A very simple problem let us consider. Let us consider a tank like this. Let us consider a tank like this. Let us consider a tank like this. Very simple problem, school level problem you can say. Let us consider a tank like this, which at any instant, unsteady problem, has, we start the instant when the height is h, or at any instant we define the tank height is h, which is a function of time. Why? Because we define the problem this way, that from two sides the fluid is flowing out with uniform velocity V1 and V2, and this area of cross section of this pipe is A1 and this pipe area is A2, and the fluid is going out continuously. And consider an incompressible fluid, a liquid whose density rho is constant. Now, this problem is very simple. I know you can immediately write if I tell you what should be the differential equation for Ht, h as a function of t. That means rather this way, if you do not write, you write h as a function of t. How do you develop the differential equation from the conservation of mass? Now, how you will use the Reynolds transport theorem? We will use the Reynolds transport theorem, we will use like that, 0 is del del T of, how this problem is solved? Very simple problem, very very simple problem in by Reynolds transport theorem, rho dV by the application plus what is this, rho Vr dot dot n dA dot n dA. Now, the second term I am writing now, rho Vr dot n dA. Now, rho Vr dot n dA is what? Over the entire control surface. Now, this here the flux is there only at A1 and A2. So, therefore, the second term rho Vr dot n dA will be written as rho. Now, Vr, it is V because it is absolute velocity, because no question of relative velocity here. Relative velocity and absolute velocity means velocity at the with respect to a reference frame which is static is same. So, unnecessarily I am not writing Vr, it is simply the V, velocity V. Let us consider the surface A. So, velocity V. Now, the surface A, the velocity V, I am just changing Vr as velocity V. n dA dot for surface A1 plus rho V dot n dA for surface A2. Now, what is V? Now, with that, when it is a vector term, better we define a unit vector in this positive direction. This direction let us take positive, arbitrarily we take this as the positive, where we define a unit vector I which is positive along this x. Now, here what happened is rho, then this V is V1, it is in the opposite direction, it is negative I, that means it can be written as minus I V1, minus I V1. Again, this the outward normal to this area is also in the opposite direction of the I, that means is a negative I, that means we can write dot minus I d A. Now, what is this here? Here both the velocity and the outward normal direction are in the positive direction of x, where we define the unit vector I. So, therefore, we can write this is as plus I V, V1, V is actually here V1 constant, I V2 dot I dA. So, what is it? If rho is constant, then rho comes out, minus I dot minus I minus minus plus and I dot I1. Now, V1 is constant, so V1 comes out. So, if V1 is constant, here it is defined as the constant velocity, then V1 comes out. So, integral dA means area, that means rho A1 V1. Even if V1 is not constant, then of course, we can write the similar thing. Instead of V1 we can write an average velocity. For example, V is not constant, then minus I dot minus I1, then V dA over the area A1, over the area A1, by definition it is V average for area A1 times the area 1 is by definition. The V average is integral V dA over the area A1 divided by the total area A1. So, therefore, we can write both in terms of average velocity or uniform velocity. Here it is given uniform. So, plus this case it will be rho A2 V2. Here also dA is V2 comes out constant, I dot I1 dA integral over A2 A2. Therefore, we can write this as rho A1 V1 plus rho A2 V2. Now, what is this first term? Del del T of rho dV. Now, rho is constant, incompressible fluid. So, we take rho totally out of integration and differentiation. So, then del del T of integral dV is the volume of the control volume, and this is the control volume. I am sorry, I did not define the control volume first. So, this is the control volume. So, we take this is the control volume. So, the control volume is equal to rho, this del del T will be now d dt A into H, total change derivative. So, if A, this A is the cross sectional area of the tank, let us define as AS, cross sectional area of the tank, which is constant. So, I take rho AS dH dt. So, therefore, you see rho AS dH dt plus rho A1 V1 plus rho A2 V2 is 0, which is equal to, from which we get that, from which we get very simple expression that dH dt is equal to minus rho 1 A1 V1 plus rho, sorry, rho, here rho is constant, rho into A1 V1 plus A2 V2 divided by rho AS. So, rho cancels out. This is a case, very simple case, that means minus A1 V1 plus A2 V2 divided by S. So, it is a very simple case. This can be done by seeing the problem at once, but how we have used the equation, that means this Reynolds transport theorem for mass conservation. I think we should go for linear momentum conservation without giving that example. We will tell you another problem, but that is for your let us consider a problem like this, that you do it if there is a tank, rigid tank is there, another unsteady flow problem, rigid tank is there, from where there is only exit leaking. The tank, a rigid tank of volume V is given, containing air at an absolute pressure P and temperature T, which is not a very important thing at initial time. Now air begins to escape from this by opening a valve. There is a valve. By opening this valve, air goes on escaping from this. The air passes through this tank. So the problem is that determine the instantaneous rate of change of density. This density is a function of time here. Here the problem is that how to find out this density as a function of time. Just I give you an hint, here also we can take a control volume like this, control volume like this. Now the problem is posed that the air is escaping from the tank through a pipe whose area is A1 and valve with a flow area of A1 and with a velocity of V1. That means A1 V1 is the rho A1 V1 is the rate of flow. Now here what will be there? It is also from intuition you can do it, but if you write the equation, then you get this Reynolds transport theorem, rho dV over the control volume, plus here also I write the same equation, rho VR. First always we start from the basic equation over the control surface is 0. Now this thing already we have proved, this will be rho into A1 V1, this already we have proved, that is rho A1 V1. So that will be rho A1, this I am not doing again anymore. Now del T of rho dV. So how to solve this problem? Del T of rho dV, you can take that control volume dV, you can take rho. If we now make an assumption that rho within the control volume at any instant of time is constant, that means it is uniform, but it changes from time to time, then rho can come outside. So the first term become del T of rho into integral of dV over the control volume is the control volume, this. So this plus this equals to 0. So this will give you the equation for the change in density, which you can do. Okay. So if the volume of the tank remains constant, then this becomes, I am ultimately doing the thing, then we can write d rho dt is equal to minus rho A1 V1, and this rho is the instantaneous rho as a function of time, which is the rho in the control volume and also the rho with which the air is flowing out. So therefore it is simply the equation V d rho dt is equal to minus rho A1 V1. Okay. So this is over. There are many other problems, but the conservation of mass is so simple, it comes from the intuition, but you develop practice, you see problems from books, from my book also, how Reynolds transport theorem is used to find this. Now we come to the conservation of linear momentum. Conservation of linear momentum. Conservation of linear momentum. Conservation of linear momentum. Now here by Reynolds transport theorem, conservation of linear momentum, the very first line is n is now m into v by definition, linear momentum, where we describe v with respect to a static frame of reference or an inertial frame of reference moving with uniform velocity. Let us consider for your understanding at the first time static frame of reference, that means absolute velocity. So linear momentum then, so corresponding eta will be v. Then I write the equation d dt of mv for the system. Now the Reynolds transport theorem, is equal to what? Del del T of eta is V, that means rho V, then VR as usual dot, which is the there for the outflow. Oh, sorry, I am extremely sorry. First term will be del del T of rho V dash dV plus the efflux, I am extremely sorry, rho V dash V R dash, rather you write like this way, N dA. This is over control volume, this is over control surface. So, this is the rate of change of momentum within the control volume, rate of momentum efflux from the control volume. That means, I am substituting N as mv, eta as V in the, and it is a vector equation, it is vector, you see V1, here also vector, this is a scalar quantity Vr dot NdA. So, therefore, it is everything is clear. Now, this is what? This is we write. Now, this is what? This left hand side, right hand side is very clear. Left hand side can also be written in consideration of the fact that the velocity is varying within the system. One can write this as, this we can write as V bar. This is another way of writing this in this system. And if we take the differentiation within the integration for a continuous function, we do that, since by definition dm or m of the system does not change with time, invariant with time, we can write dv dt dm this system. That means dv dt dm of this system, this is the same thing, d dt of mv. Now, if you see that V, this m is the system mass, V is the velocity at each and every point of the system. So, therefore, we see that this dv dt, if this is varying with the system, then we can make this integration. Okay? If dv dt comes out, then dv dt into integral dm is m dv dt, which is coming from here also, m dv dt. M is constant for this system, m dv dt. But we can write integral dv dt dm in consideration of the fact that dv dt, that is the rate of change of velocity, may vary within the system. But however, this term which is derived from this term, both the terms represents the rate of change of momentum of this system. Rate of change of momentum of this system, where the velocity in the momentum is described with respect to an static frame of reference or inertial frame of reference, and by Newton's second law, this is the sum of the external forces. From Newton's second law, the sum of the external forces equals to the rate of change of momentum of the system, where the momentum, the velocity of the momentum, velocity defining the momentum is described in a static frame of reference or an inertial frame of reference. You know that when the frame of reference is at rest or moving with the uniform velocity. Here we are considering at rest, for example, then this case the rate of change of momentum of the system is the force, and that becomes equal to del del T of rho V dV, again I write Cv plus rho V Vr dot N dA. That means, I can tell this is the linear conservation of momentum with the help of Reynolds transport theorem. That means, linear conservation of momentum for control volume. And what does it state? This net force acting on the control volume. Now, here another concept is there. This rate of change of momentum of the system is the force acting on the system. And since we have already told that we have derived the Reynolds transport theorem when delta t, the time approaches 0. In the limit delta t tends to 0, the system and the control volume coincides each other. So, therefore, at any instant of time, the force acting on the system equals to the force acting on the control volume. So, therefore, we can tell the conservation of momentum principle for a control volume like this: force acting on a control volume equals to the rate of change of momentum within the control volume plus net rate of efflux or outflow of the momentum from the control volume, provided the velocity defining the momentum is described in an inertial frame of reference, static frame of reference or frame of reference moving with uniform velocity. Now we will explore what happens if the frame of reference moves with varying velocity, which is known as inertial frame of reference. So, this is the conservation of momentum for control volume when the velocity is described in inertial frame of reference, and this is known as momentum theorem. Momentum theorem. Now, you see that the question comes, let me first tell you, we are happy that this is the momentum theorem we have derived, but why are you interested to see when the velocity is described in a non-inertial frame of reference? What is non-inertial frame of reference? When the frame of reference moves with an acceleration. This is because in engineering analysis, we have to define quantities for our ease of analysis with respect to a control volume, because we consider the engineering appliances or equipment as the control volume. So, mass flux, for example, coming in or going out of the control volume is defined based on the relative velocity of the control volume. This has to be there, otherwise you cannot define the mass flux. From a moving system, if some fluid goes out, you can tell that what is the quantity going out, area into velocity, that velocity is the velocity relative to the equipment or the instrument or the device from which the fluid is going out. Similarly, in case of fluid coming in. So, therefore, we always attach the coordinate system with the control volume, and in some cases it has been found this control volume is accelerating. If the control volume is always at rest, for example, a power plant condenser, boiler, compressor, turbine, these are absolutely rest, equipment at rest, we are very happy. Okay. So, we are happy with the equation that where the Reynolds transport theorem describes the conservation of momentum for the control volume known as momentum theorem, where velocity is described with respect to a inertial reference frame. We are also happy, for example, a jet engine or aircraft moving with a constant velocity, then also we are happy, because if we attach the coordinate axis with the control volume, the control volume is moving with the uniform velocity. There also this thing will hold good. But if it accelerates, the jet engine accelerates. In case of rocket, rocket has a great acceleration when it goes up from the at the time of its launching from the ground. So, therefore, in case of accelerating rocket, accelerating jet engine and many other devices which accelerates, the control volume is accelerating, and at the same time the things have to be described for ease of analysis with respect to the control volume. So, therefore, question comes, what will be the shape of this or equation when we define the velocity with respect to the control volume. Now, let us see that. Now, let us consider a control volume like this, where we attach the axis with the control volume, and let us consider the control volume is moving with a velocity VCV. VCV is the velocity of the control volume. That means the velocity of this, and we consider this is a linear velocity and VCV is a function of time. That means there is an acceleration of the control volume, which is nothing but dVCV dt, which is also linear. That means the control volume has a rectilinear acceleration. That means the frame of reference has a rectilinear acceleration, for example. Now, what will be the case? Now, the case will be like this. If we write now this equation here, we will see that d dt of, now I write with respect to the control volume. That means our velocity now is reference to with respect to the control volume. That means we write this is VR. That means VR. I defined earlier VR is what? With respect to the control volume. Now, we give this nomenclature where V with respect to a, let us consider capital X, Y and Z is the static frame of reference. With respect to the static frame of reference, V minus VCV. This is our relative velocity, when this frame of reference attached to the control volume has a rectilinear motion and acceleration. So, then d dt of m Vr system equals to what? Equals to del del T of over the control volume rho. Now, Vr dV plus rho Vr dot n dA, that means rate of F flux. That means what I am doing here, the property is m Vr. That means the momentum is defined in this way, that Vr is the relative velocity. Okay. Everything on the right hand side is same, only V is replaced by Vr, here also that. But can I write this as the sigma f? No. Let us write in terms of variation of the property, which we wrote earlier also, that means integral Vr by dm, and in consideration of the fact that dm is invariant with time, in the similar way this is system, we write dVr dt system. The only difference with the earlier way, that earlier it was V, earlier it was V dV dt dm, mv dV dt, and we wrote F, F on the system which equals to F control volume. But can we write this here? No. When we can write? We can write when Vcb is constant, because by Newton's law the rate of change of momentum equals to the force on the system, provided this velocity is described in a static frame of reference. Now, if Vcb is constant, then Vr dt dV dt is same as dV dt. That means, if the frame of reference or the control volume where the frame of reference is attached to it moves with the uniform velocity, does not matter, because acceleration with respect to the control volume and with respect to a static frame of reference is same. But if this has an acceleration, then dVr dt is equal to dV dt minus dVcv dt. Okay. So, therefore, we can write this d dt of dV dt minus dV Cv dt, which is the acceleration, into dm. So, therefore, I can write this, I will keep this here, otherwise you will have problem. I think you can see this. Now, you can write this. So, therefore, this thing now I am doing that, this you can write d dt of, sorry, d dt will not be there, integral this, it is system. So, therefore, this will be system, again I am writing dV dt dm minus over this system dVcv dt dm. This now by the earlier principle is sigma f. And what is this? This is as usual system dVcv dt into dm. Now, this system coincides with the control volume. So, therefore, we can write this f, actually this is the control volume acceleration. So, from here itself we can write this as the control volume. So, does not matter, this over the control volume minus this, and if this is the acceleration, so we write this nomenclature of the control volume dm with the coinciding control volume. If the acceleration within the control volume is constant, then this can be further simplified as minus acceleration comes dm, that means mass of the control volume into the acceleration vector. So, this is the modification of the left hand term. That means right hand term we just replace the absolute velocity as the relative velocity, since we define the momentum based on the relative velocity. But when we do this in the left hand side we cannot replace by external forces by Newton's second law, since the momentum is not described or the velocity of the momentum is not described in a inertial frame of reference. So, therefore, we have to substitute this where dvcb dt is not 0, which is the acceleration of the control volume, and there what happens, the left hand side gets a change, this minus this. So, this is the sigma of the external forces on the control volume minus acceleration times mass integrated over the control volume. If control volume has the constant acceleration at all points, what usually happens, the control volume has an acceleration, unique acceleration for all each and every point. Control volume acceleration is same, not changing from point to point within the control volume, so that I can take it out. So, simply this. That means, we can write that in this case sigma left hand side there will be only a change sigma ACV is equal to the right hand side. Again I am writing will be the same del del TR. Here rho, either you write VR or you write V, does not matter. When you write V, then this thing is 0. When you referenced it with VR, then this thing will come. That means when you write the velocity with respect to a inertial frame of reference, static or moving with uniform velocity, then this will be 0. Similarly, plus the net rate of a flux term, that means rho VR, when I write in terms of VR, VR dot NDA. But if I write it in terms of V, the absolute velocity, then obviously this term will be 0. That means, when it is absolute velocity, force acting on the control volume is net rate of change of momentum within the control volume plus net rate of momentum efflux from the control volume. But when the control volume is moving with an acceleration, then sigma fc be the force acting on the control minus the mass of the control volume in the acceleration of the control volume equals to this thing, the rate, the increase plus this. Huh? This is dV, sorry, very good, dV. Well, so this is the linear momentum, conservation of linear momentum, where momentum velocity in the momentum is described with respect to an inertial control volume and also described with respect to a non-inertial control volume. Afterwards, we will solve problems showing both this thing, inertial and non-inertial control volume. I think take 2-3 questions. I think today we will stop here. We will start the conservation of angular momentum tomorrow. Or should we introduce conservation of angular momentum today? Better take 2-3 questions, time is there. I think rather at a time so many things to be told, better we take some questions. Okay. 1 to 4. Please ask question. Yes.
Hello sir, myself BQ
Okay.
from Bhopal.
Okay, fine.
Sir, my question is that, sir, good afternoon to you, sir.
Good afternoon, please.
Question is that
Please ask
the
question.
steam is flowing in a pipeline. We are using current meter and rotameter for measuring the flow measurement. How to apply the Bernoulli equation for the compressible?
For
the
the
fluid is compressible and we can use the flow measuring.
No,
device
this
to
question,
measure
hello, this question you ask in the next session, when the question answering session will be there, and Professor Suman Chakraborty, who has already taught this, he will be answering this question, how do you apply the Bernoulli's equation for compressible flow, that everything will be told. But I tell you one thing, in a rotameter is already graduated with respect to a particular, if it is a gas, with respect to a particular pressure and temperature with a reference density. So, you have to make a density correction factor for that measurement based on the compressibility effect. That is true. That will be told by Professor Suman Chakraborty. Okay. And that will be at the end of the session. But now I will entertain questions because time is there for my session, whatever I have taught, because there will be a tea break. After that we will be having a question answering session where Professor Suman Chakraborty and Professor Ghosh Mollik, who have taught this part of inviscid flow and its application, they will be they will be here to answer your questions. But now before going to tea break, I like to know if you have any doubt regarding the materials which I have taught now in this session.
So
Okay.
my second question is, what is the difference between stagnation, static pressure and total pressure?
Again I am telling, this is not been taught at this moment. So static pressure and total pressure, there is a difference that will be again answered afterward. Total pressure is the pressure when the velocity of the fluid is converted to the pressure. If a fluid is brought to rest, then the kinetic energy is converted to its pressure. But total pressure, a stagnation pressure we define theoretically as the pressure if the fluid stream is brought to rest isentropically. That means when a fluid stream is brought to rest, what happens? The kinetic energy is converted both in terms of pressure and also being dissipated as intermolecular energy, which makes that fluid heated, and that is lost from the mechanical energy part. But if we make it isentropically without any friction and without any heat transfer, so therefore what happens? The entire kinetic energy is being converted into pressure, and that pressure plus the static pressure means added together is the total pressure. But I am not going to answer this question at this session. Please ask question from what I have taught now in this session. Next.
Yes. Thank you very much, sir.
Okay. 1252. 1252 R RC RCIT 1252.
Hello.
1252.
Hello, can you hear me?
Yes, I hear you.
Hello, can you hear me?
Yes, yes, I hear you.
Hello.
Yes, yes, please.
Hello,
I can
you hear me?
I can hear you.
Yes, sir. Sir, I have got a doubt about collapsible control volume. Collapsible control volume.
Now, okay, this is your question.
I have got a doubt about.
Okay, now I answer
got-
your. Okay, I answer your question. Okay, I have got your question. Okay, okay. Now here
Yes, I
in the
have got a doubt about collapsible control volume.
okay, okay.
Sir,
Let
whether that is applicable for deriving a law of conservation of momentum, just you have told about.
okay. Let me answer. There is no collapsible control volume which has been taught now. Try to understand here what has been taught. There is a control volume and the system. It is the mathematical technique that when we define at an instant the things, the phenomena, what we call, what we do, we have taken after an infinite small time delta t when the system has approached, system has progressed, approach or system has progressed to some extent where there is a difference between the system and the control volume. They are not coinciding, but when delta t tends to 0, then the system and control volume ultimately coincide with each other. Then what is collapsed? The intercepted area is collapsed. You understand, it is the concept, mathematical concept. Control volume is not collapsing to 0, system is not collapsing to 0. You understand that these collapses means this comes to a point when you do in the mathematical analysis, you have understood that delta t limit tends to 0, system and this coincides, that the intercepted volume collapses. Okay.
One two five eight.
1258. 1258. 1258.
Hello.
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 Hello, please.
Sir, good afternoon.
Good afternoon.
Hello.
Hello. Yes.
Hello.
Hello.
Sir, good afternoon.
Good afternoon.
Hello. Sir, 1258. Ajay Kumar.
Okay. Please tell.
Sir, what is the use of stagnation point?
This will be answered afterwards. You please ask questions whatever has been taught from this session.
Yes, sir.
You please ask questions from whatever has been asked in this session. I have left this time before tea. Why they have asked?
1253.
We have to announce that. 1253. Please ask questions from whatever has been told from in this session. If you have any doubt, I will entertain only those questions before tea which pertain to your doubt with respect to the coverage of this session, whatever has been taught in this session.
Not audible.
Not audible. Please tell, not audible.
1314.
1314. 1314. 1314. Next.
Hello.
Hello, please.
Hello. Good afternoon, sir.
Good afternoon. Please.
Sir, sir, what is the Vena contractor in case of the Venturi meter, sir?
That you ask afterwards, after tea session. There will be Professor Sandipan Ghosh Mallik who will answer this. Okay. But I can tell you Vena contract in Venturi meter is the throat section, the minimum area.
1064.
1064. আজ প্রচুর কোশ্চেন করবে এইসব ভেনা কন্ট্রাক্ট
You are-
হ্যাঁ
You are not audible.
You are not audible. You are not audible. Any other?
330 dot zero.
330 তে ছেড়ে দিও যা এরা তো রেনল্ডস ট্রান্সপোর্ট থিওরেম বুঝেছে কিনা সন্দেহ
Hello.
হ্যালো
Hello, good afternoon, sir.
ইয়েস গুড আফটারনুন
Hello.
গুড আফটারনুন
Sir, yesterday you explained the angular deformation, rotational and circulation.
সার্কুলেশন আই
In that
ডিড
case,
নট টেল
how
ওকে
Circulation is different than the rotational.
Circulation
flow.
is different. I have not told circulation. Okay, please tell. Please.
How circulation is different than the vorticity?
Circulate.
Is there any relation between
Yes, there is
circulation
a
and vorticity?
yes, there is a relation between circulation and vorticity, which will be taught by Professor Sandipan Ghosh Mallik afterwards. I tell you, the vorticity is defined, which has not been covered so far. It will be done afterwards. But I tell you now, when you have asked the question, that vorticity is defined as curl of the velocity vector, which is twice the rotation. So, concept of vorticity comes from the rotation of the fluid element. You understand? That is defined as twice the rotation, that is curl of the velocity vector. Circulation is defined in any fluid path. If you take a closed contour, then the line integral of the velocity and product of the velocity and the line element, that means if velocity is v and a linear element is ds, then the v dot ds, the integral, cyclic integral v dot ds over a closed contour is defined as circulation. And circulation and vorticity has a very good relationship, and that relationship is like this: the circulation over a closed loop is equals to the vorticity per unit area. That is the relationship. Circulation is vorticity per unit area. You have understood that?
Sir, in case of circulation, there is any difference between circulation, rotational flow and circulation?
No, there is actually rotational flow, irrotational flow is different. Circulation is another thing. Circulation is another specific parameter of the flow. Okay? This thing will be told in detail. So far it has not been told in detail, that is why you have not understood. Just I told to quench your inquisitiveness, but it will be taught in detail by Professor Ghosh Mollik and then it will be clear. I have told this is the relationship between circulation and vorticity. This is known as Stokes theorem. Okay, this is known as Stokes theorem, that line integral of a vector, relationship between the line integral of the vector and surface integral of the curl of the vector. Okay, you read that Stokes theorem. Okay.
1330.
1330.
Hello?
Please.
Hello?
Please.
Am I audible, sir?
Yes.
Sir, may I have a question?
Yes.
Please describe the physical and practical application of Reynolds transport theorem for non-inertial control volume.
Non-inertial control volume, the practical applications I told. In tomorrow's class I will solve a problem when the control volume is accelerating. For example, when you apply this conservation laws to a jet engine which is moving with an acceleration. Okay, you understand that. Also for a rocket engine where there is an acceleration, you try to find out the applications where the things are moving with acceleration. In case of a ship which is moving with an acceleration, if you find out the propulsive force to a rocket engine, to a ship, to a jet engine which are moving with acceleration, not moving with constant velocity, you have to apply this non-inertial control volume. Okay, clear? Next.
Hello.
Okay.
Hello.
Yes, please.
Hello?
Please.
Yeah. May I ask you a question, sir?
Yes.
Sir, a very simple clarification on the two topics, the microscopic approach and microscopic approach. Just I want to be clear on these two approaches. And then how do we define the fluid element or fluid particle in a fluid flow?
This question has been answered several times. I tell you, microscopic approaches are the approaches where we find out the properties of a fluid from the molecular behavior, from the statistical average of the molecules, a group of molecules. In a macroscopic approach, the same thing is done, that is the statistical average of the molecules are taken, but not from the molecular studies, but directly from the measurement by an instrument which sends this gross average molecular behavior in manifestation of the property, and then we use this property and by the application of differential equation we resolve this and we find its change with space coordinates and time. This is the macroscopic approach. Okay. Difference between fluid particle and fluid element. Particle means what? Element is an element which has got some finite volume, finite mass, whatever small it may be, and particle means of zero mass and zero volume. Okay. Any other?
Hello.
Hello, please.
Good afternoon, sir.
Yes.
Sir, you have in the derivation of Reynolds transport theorem, you have shown
Yes.
at time t plus delta t,
Okay.
system and the control volume is changing.
Changing.
So, in the physical example, in the example that you have shown the second time, I think some aeroplane example you have told, the frame of reference is changing. Second example, please make it, will you please make it once again that clear, sir?
Which one? I
This
could not.
example we understood, that is a tank is there and the second one.
No, I cannot understand. I cannot follow your question. What do you want to know?
Sir, at time t, system
And-
and control volume is coinciding.
Okay.
In the derivation you have shown that.
Okay. And time t plus delta t, there is a displacement, yes, between the control volume and the system. System has moved somewhat, yes. Okay.
Yes, sir. So now, in the first example, in the second example, what is exactly the control volume and what is the system? Like
No
when
system,
it translating and when
everything is
it
control
at
volume.
time t plus delta
Sec,
t, how it is changing. That
no, no, second,
physics we did not understand.
of second,
Example.
second example or first example, all the examples given for mass conservation, there was only control volume, no system. You understand? Try to understand. We have done everything with respect to a control volume. The tank itself is a control volume. Let me show you. No, no, this example you show that. This is a control volume. This tank is a control volume. I tell you, this example, this is the tank, this is the control volume. This entire thing is the control volume. No system. Then another example was that there is a tank and where the fluid is coming out only by opening a valve, then this is the control volume. Try to understand that we have used both system and control volume in Reynolds transport theorem to derive the relation between the statement of the conservation laws applied to a system to that applied to a control volume. When we achieve this, then what happened? We get this thing, because what we do, the change of some property, for example mass, for this system we know we put it at 0, and at that instant mass and control volume coincide. That means it is 0 for left hand side and then right hand side, these are for control volume. So then the equation represents that for a control volume. You understand? Similarly, for a conservation of linear momentum, the left hand side represents the rate of change of momentum of a system. So therefore, it is replaced by the law applicable to system as the net external forces applied to a system if the velocity in the momentum is described with respect to an inertial frame of reference. But the right hand side, the quantities are for a control volume, and since in a limit delta t tends to 0, control volume and system coincides each other, this force exerted on a system means exerted on the control volume. So therefore, the entire equation of conservation or the statement of conservation of momentum is valid for the control volume now, okay, which is known as momentum theorem. There is no system in the example. Okay. Okay, now I am going, we will take more questions related to Reynolds transport theorem tomorrow in the question answering session, when I will be completing the Reynolds transport theorem in tomorrow morning's lecture session. Okay, thank you. Thank you.